Good morning, everyone. We will tackle today continuation of what we started last time in the form of performance measure for machine learning models. And this is an important component in this course because it provides us with the ability for generating some information about how to have a qualitative type of assessments of a particular machine learning, whether for classification or for regression. Before I start the lecture, I have a few announcements that I would like to make, and I will also email you about them. The first announcement is related to the fact that during our quiz time, I will give 10 minutes beyond the 1 hour. So we will start the exam or the quiz at 10 a.m. And then we will start 10 a.m. for one group. And also we started for the second group who are overseas and in different time zone at 9:50 p.m. So that to help you out, prepare yourself and prepare, the setup for your quiz. So you have basically 1 hour for the quiz, and if you are well prepared, the quiz should take you less than 1 hour time. But I will give you 1 hour for that, and then I give you also 10 minutes besides that. So that's one item that I wanted to mention about it. I will post today, in possibly within the next 2-3 hours. The material on the solution for the quiz test that I have shared with you yesterday. So I will provide the solutions, and then I will also provide you with the presentation material for tutorial number 3, where my TA Mahmoud has gone over a problem in the area of classification, which should help you, especially with problem number 4. So these all items that are going to be posted within the next 2 to 3 hours, and I will send an email reminding you of that. So that's basically for what we are going to do. And the quiz will cover material up to the end of this section, which is performance measures. So it's not going to include any component on support vector machine, which I'm going to start tackling today. So please take a note of that. So that's what I wanted to share with you. One more comment here, and I would like the whole class to be aware of it. Please utilize Piazza only when you need to utilize it. Only in really when you need help, because me and my TAs are overwhelmed, literally overwhelmed, and I don't know what to do. I might even lock the system or whatever, but I don't want to do that. But we are overwhelmed with requests. Some of these type of requests are minor. And please only post when you are in real need of support or help, because I know that other classmates might not help you immediately, but I try to do that in real time. But I am overwhelmed. I have so many other tasks myself besides teaching the course, and I am enjoying providing you support, but I am overwhelmed, me and my TAs. So please only use Piazza when you need to do that. If you have a specific question about coding or about something that you need, that it's not going to benefit your other classmates, please email me or email any of my TAs, and I should be replied to you very, very, very quickly. But utilize Piazza only when there is need to do that. So I would like it to be a medium to help you out, but only when you need to do so. Okay, so that's the few items that I wanted to share with you. Now going back to our lectures here. So let me go here and see what we have here. So one page display, so single page. So last time we started talking about classification performance measures and how we are utilizing them for resolving a number of problems and a number of issues when we have a whole set of models with which we would like to do certain type of qualitative assessment. So when we speak of qualitative assessments, and you have, I think, this wording in the course, that's what I meant. Basically, assess models according to what you need to utilize for that particular type of model. So basically, when you have a particular model for the system, there are a number of performance metrics that you may need to utilize and you may need to use to say that this model is better than the others. And we spoke, especially for the classification part, with the confusion matrix of 2 by 2, where we have a binary classification. And we mentioned that the recall measure is not always the one to use, and the precision measure is not the one to use. It depends on the problem at hand. So I provide you with the spam problem. In the spam problem, it is very important to have the precision measure as for the system. For the recall measure, we use it, for instance, for the infection case, where we would like to minimize the false negative type of classes. So remember, when you need to classify the false negative for a particular class, always utilize the recall measure. When you would like to minimize the false positive measure, always utilize the precision. This is in general, okay? And we saw that the F1 measure integrates between both recall and the precision, and it provides always, I mean, it's at the lower end of either one of the precision or the recall, so the F1 measure is close to the lower value, whether it's a precision or the recall for a particular class matrix. I haven't spoken about accuracy. Accuracy usually is an excellent measure as well when the classes are balanced. Let me explain what we mean by balanced. Balanced, it means that we have almost equal classes for yes or no, for false or true. So when we have a balanced number, so we have 50-50 or even 60-40, accuracy sometimes provides you with a good measure of performance. But if you have very, very small number of false class or and large number for true, or vice versa, you have false large and the true is very, very small number of entities, then don't use accuracy. Accuracy doesn't help you. And in some of the examples that I provided in the additional reading, it provides you with certain type of examples in that regard. So let me go now and talk a little bit more about the example 3, which is a measure for classification performance for a multi-class. It's not only binary, so now we are dealing with multi-class. So multi-class, when we have several type of labels. What we mean by labels, I mean here are the various type of classes. So let me go over this example because it's an important one, and this is also material related to the quiz as well. So as I mentioned to you, all material related to the set performance measure is, I mean, part of the quiz. There is also one question in the test quiz that I provided you. So the actual label means that this is the real world, what we have in the real world. So those are the, like what we call it, target when we tackle the perceptron and the adeline. The predicted label is what the classifier provides us. Whether it's true or false, that's what the classifier tells us. It's whether the class is correct or not correct. So let's look here at 3 types of dogs. So we have the golden retriever, we have the Samoyed type of dog, and we have the Mastiff type of dog, okay? And for the golden retriever, we have, I mean, the predicted label from this side and the actual label from this particular side. So let me go here to comment because I need to do certain type of, from time to time. So we have the actual label for this particular case here, and we have the predicted label, what the classifier provides us. So this is what the classifier provides us in terms of the measure. So what it means here, it means that the classifier provided us 14 correct answers among all 20. Remember that the golden retriever here, the number total is equal to 14 plus 5 plus 1, which is the 100% number of the golden retriever. The Samoyed one, So this is what the system provided us in terms of the predicted level, but also the system provided us with a false positive. So golden retriever, so this is, I mean, wrong one here. So this is, I mean, it should not be this particular value in this particular case. The mastiff here provided us with 0, but it is actually 0 in this particular case. So the predicted label provided us with 17, correct one, but also provided us with a false positive 1. So false positive because we classify it as the samoyed, but it's not. It should be a golden retriever. So this is, I mean, a false positive. This is also a false positive. If we look at the false negative for the samoyed, which means that the system predicted the samoyed, but the predictor provided us with the 3 here. So this is, we call it false negative. This is a false negative with respect. So this is Fn. This is Fp. So the system is not the samoyed, but the system provides us with a predictor in the mastiff that is a false positive. So it's a false positive. It should not belong to that area. And here is the false negative. So what it means that the system should be in the samoyed. So these 3 should have been here, and this 6 here, or 9, I think the number, should have been here. So these are false negatives. So they were classified as golden retriever, but they are not. They should be samoyed. So this is a false negative here, and this is false negative here. Okay, so as you can see here, what I did, I took for each one, for this particular example, the example for the samoyed. So we could do it for the golden retriever as well, and then everything in the row is going to be perceived as false positive. Everything in the column will be perceived as the false negative. So this is how we are defining the confusion matrix for a multi-class system. Okay, so this is an example here. So for the mastiff, let me continue. For the mastiff system, so we have a true. The system has classified the true ones because you have the predicted value is here, and the mastiff here is completely true. So we have 19 well classified elements, but we have one that is classified, which should be a mastiff, but it was classified as samoyed. So this is basically, we can look at it as a false negative with respect to this particular class. Okay, so that's how we compute them. So here we are going to calculate the various performance metrics here for the true positive, for the false positive, true negative, and false negative. So for the golden retriever, for this particular type of matrix, so remember that the matrix stands, so this is, so let me go back here. So this means C11. So this is the first column and first row. So this is first. So it's third row, and so this is first column and the third row. So this is 1, 1, 1, 3. So this is 3, C, 3, 3. Okay. Okay. So this is the actually third row and third column, and this is, sorry, and this is third row and first column. Sorry for that. So this is C1, so this is C21, this is C13, so this is C13, first row, third column. Okay, so this is how we are defining the matrix here. So this is for the true positive, we have C11. Okay, for the samoyeds, we have the C22. For the mastiff, we have C33. So all of these ones are located here. So C11, C22 here. Okay, and this is C33. So for the true positive, we have all these particular values. So that's how we define this particular table in order for us to follow the same notation. So the false positive for the golden retriever is equal to C12 plus C13. What does that mean? This is false positive with respect to this particular animal. So the golden retriever here, so this is the true positive, but here it's a false positive with respect to this particular class. this is also false positive with respect to the golden retriever. So as you can see, within the row, you have false positive. Within the column, you have false negative. Remember that this false positive was for this particular entity here, which is C22 and related to the samoid. So this table expresses very well the values for the false positive with respect to this class. This is false positive with respect to the samoid here. And this is the class, the mastiff. This is the true positive. This is the false positive. And this is the true negative. So if we look at the true negative with respect to the mastiff, so this is the area. So the true negative is everything that is not related to the mastiff component. So this is what we call it the true negative. And the false negative, it's the one that is located within that particular component. So this is the false negative for this particular one. So this is false negative with respect to the mastiff. This is false negative with respect to this value. So once we understand this particular representation here, we calculate the various performance metrics for this particular system. So let's look at it, I mean, in this particular way. So for the true positive, for the particular class, we have 14 here, we have 3 here, we have 37 here, we have 34 here, and we have 3 here. The mastiff, we have true positive, 19, we have 1, and 39 here because of the entries in the earlier slide, and the false negative. So if we look at the mastiff class, so we have here true positive. All of this is considered as true negative, the summation of all of them, 17 plus 14, 31, plus 3, 34, plus 5, so it makes it 39. And then these are the false negative with respect to the mastiff. These are the false positive. So that's, I would like you to remember, within the same column is the false negative. Within the same row, it's the false negative with the false positive with respect to that particular class. So if we understand this type of labeling, I mean, we should do fine in terms of computing these values. So make sure that we understand this and to have these particular numbers if you are going to recall this particular example. So these are the definition for the true positive and the true negative. So now would like to call now the various type of measure for the golden retriever. So now we have defined the false positive for it, the true negative, the false negative, and the true positive. And then we utilize exactly the same formula that we have used before. So here we have 0.85, which is 85%. Precision is 82%. Recall is 70%. So the recall is less than the 0.82. And we should expect that F1 measure is going to be in between the recall and the precision, which is exactly the case. So which is 0.76. So I would like you to go through this example again. It's very well defined. It is, I mean, the labels are very well structured there. And I would like you to reproduce it to make sure that you understand exactly what we mean by this performance measure. So this is how we define this performance measure for a particular class within a multi-class system. If we understand this representation, then you should be able to do it. And problem 3 could be one of these cases. You may need to apply for problem 4, actually, the classification problem, how to obtain these particular characteristics or performance measure for our system. So let me, before I go to the next part, so if you have any questions here, so let me see if there are any questions so far. Let me know and I will be happy to answer you. Okay. I still encourage, I know that a number of you are not able to attend the lectures, I mean, synchronously, but I still encourage you to attend the lecture with me. I'm spending, I mean, the time here, I mean, real time, and I would like you to follow up with me. If you have some question, I will be happy to answer you, to answer these type of questions. Any questions or any hand raised here before I continue? Okay, so I don't see any hands here, so I will continue. I will also give you the opportunity at the end of the class. I will give the last 5 minutes of the lecture. If you have any question, I would be happy to answer you, whether related to this lecture or any other type of material. So we have a full 5 minutes at the end of the lecture to tackle these particular questions that you may have. Okay, so here, when we are going to do what is known as performance measure versus for all versus all. So what does that mean, all versus all? All versus all, it means that how cumulative the performance measure is going to be for all the classes. So in the earlier slide, we tackled one single class, the golden retriever. We could also tackle the other class, which is the mastiff. But we did it for one particular class versus all. So this is what we call one versus all. Remember, one versus all, it means one class versus all the other classes. However, there is the cumulative, the all versus all. The all versus all, especially where we can also talk about accuracy, when we talk about the number of correct precision predictions. So the true positive here is the true positive cumulative for all the classes. For the mastiff and for the golden retriever, for every class, we accumulate all the numbers. And we find that the overall accuracy of all versus all is equal to 83%. For the precision, we do the same thing. We add up all the true positive, which are equal to 50 here, okay? And these particular values also, we divide them by true positive plus false positive for all the system, okay? So these are the values for the precision. So we have 83% here. And it happens that in this particular case, the precision is equal to the recall. Sometimes we have those particular values. And then, of course, because both of them are equal, so we find that the F1 is between two values that are equal, and it is equal to 83%. Okay, so usually when we are doing all versus all the measures, the accuracy, the precision, the recall, and F1 measure, all of them are equal. Okay, so this is one particular characteristics of all versus all. So if you find one particular characteristics of the measures for all versus all, then one of them leads to every other metric. But it is not very well used type of characteristics. I mean, although it is easy to compute here, but it's not very well used. It doesn't give us a lot of information about a particular class, how it was classified versus other type of classes. Okay, so that's one note about one versus all versus all versus all. So if I ask you in an example to compute for me the accuracy or precision or recall F1 measure in a particular measure, do not waste your time for all versus all. Accuracy is equal to precision is equal to recall is equal to F1 measure. And that's the end of it. For one versus all, you have to compute each one on its own. That's more, I mean, time consumption. Okay, so this is basically what I wanted to share with you here for the performance measure for the classifier. So all what we have seen in the last lecture and in this lecture so far is related to classifier, which means discrete output of the engine of the neural network model or the machine learning model. So this is, first of all, a supervised machine learning model based on connectionist modeling. That's what we have been doing so far. And we have measured these particular type of characteristics. First, we inferred the confusion matrix, whether it's for binary or for multi-class system. So confusion matrix for multi-class system. And then we inferred as well the values for the various components in the form of the performance measure, which are the qualitative type of measure. So whenever I speak of a qualitative measure, so this is what I mean. They are the accuracy, the precision, the recall, the F1 measure, and you can only do this once by constructing the confusion matrix. So that's what I wanted to share with you. I mean, I won't go further. There are a number of other parameters that people utilize, but because of the restriction of time, we won't go over it. I gave you the major characteristics for performance measure and the qualitative measure. So now we have done it for the classification. So let's do something for the regression. Remember, problem 3 of the assignments is a regression-based model. We spoke about the overfit. Last time we spoke about the underfit for regression and for classification. So today we are going to speak a little bit about qualitative measure. Qualitative measure. What are the major qualitative components for regression problem? Okay, so this is what we are going to discuss. One of the major qualitative measure is what is known as mean squared error. What is the mean squared error? Mean squared error is simply the difference between the real value which the system has, I mean, it has a priori from training or from testing, and what the system provided us using a particular model. So this particular model here, it's a linear one, but we could have a polynomial regression, we could have a nonlinear regression that came out from the engine of a neural network system. So this is, again, so we compute the difference between this one and this one, okay, and then we create what is known as the mean square error. Why we put the squared here? The squared is simply to not making a difference between whether the value, the real value, is below the curve or this is the model that we have created. So this is your model between the real values and the model itself. So whether it is here negative or whether it is here positive, it is going to be the same because it's going to be squared. So it's yi minus yi hat. So that's why we have the squared. And then we take the average, how many values that we have computed, 1, 2, 3, 4, 5, 6, 7 in this particular case. So we sum up all these errors here, okay, 2, 3 error, 4th error, 5th error, 6th error, 7th error, and then we take the average. So that's as simple as that. That's the mean, and that's why we call it mean, because we take the mean here, the average for this particular square, where the high error get bold because of the power 2 for this particular system. That's this particular type of representation that we are computing the yi minus yi hat to square root for these particular values. So that's, I mean, as simple as that, mean squared error between the training or the testing, because remember that we have training data set and we have testing data set. So if we are going to do between the training and the real model, so this is how we compute it. So this is for training. So it becomes mean squared error for training. And if we have these particular values are the tested value, then it's mean squared error, MSE, for testing. So that's when I speak about the error for in the example or in the assignments, it means mean squared error of the testing and mean squared error for the training. So that's what we mean by those particular qualitative type of values. There is also the root mean squared error. Sometimes people utilize these particular values. I mean, there is no reason why people use it, but some people, I mean, I mean, this of course are going to be smaller type of values, and in the particular case where the value is very, very small, this will give us even larger values because the square root of very small number, it's the higher value of the number. So if you have 0.0001, the root mean square error is going to be a little bigger value. So for plotting or for comparison with other type of approaches. So both of them have been utilized, and in the assignment you can use either one of them. The root mean squared error or the mean squared error, both of them are equivalent. Okay, so there is also what is known as the mean absolute error. Also, this has been utilized, and it's similar to what we have in terms of the mean squared error. The only thing here, we don't compute the squared. So if the error is already small, we don't need to compute the square of it to make it even smaller. And certain time for computational purposes, it becomes very small value. So we don't want that to happen. So what we do, simply we take the absolute value. So whether it is located here or it's located here, it's going to be the same particular values, okay? And then we take the average, as you can see here, for this particular value. The mean absolute error measure, which is most robust to outliers than mean square error for a particular system, because it doesn't have the power 2. So what we mean by outlier, when values are far away from the particular type of curve, so you don't this particular error is going to showcase it, that is, showcase that particular value. If it is very, very far away, then this particular value becomes far away. And it showcases that it's going to have a big weight in that particular representation. So that's why we call it more robust. So I don't have any type of preference in this particular assignments, but people have been using most of the time mean squared error. For the programs or for the platform that you are going to use when you are going to program these particular values, I mean, there are many of the Python or TensorFlow or other type of platform to help you in the computation have all these particular errors, and you simply search for them in that particular software and the system give them to you readily. So you give the values where you would like to compute, and the system provides you immediately with these particular values. Okay, so there is what is known also the median absolute error. People did not use it, I mean, much, but especially for the outliers, again, for values that are far away from, I mean, from the main curve, people have using the median absolute error. So it's up to you to utilize which one. Median absolute error has been not used in a lot of cases, but it's simply when you have large outliers, basically several type of values that are not within the close region of the model that you have created. Remember that the model here is linear. The model could be nonlinear as well. You could have something like this, and still you are going to compute the distance between the model itself and the particular value. So continuing, I mean, this has not been used much in the literature, but still, people, I mean, if you are asked to compute it, you should know how to compute this particular value, and the median is going to be the median among all those particular values. So it will be representative, if you would like, of these all this particular value, and it has, I mean, it gives you where the median of the various particular values of the errors are located. So this is to situate large values that may happen sometimes to be in the median of the absolute error. Okay, the R2 score, from time to time you hear about the R2 score. This is the R2 score. What do you mean, or the R score? The R score is the square root of this particular representation. What is the R2 score? The R2 score is basically normalization of the error from the mean of the data. So the data has a mean. Basically, it's like an average of all the data, but this one normalizes the distance between the training and the testing data from the mean of the data. So it gives you a certain good idea where the location of most of these estimated values, which are green in this particular case, with respect to the mean of all these particular type of data that we have measured. So all this data have a certain type of mean. So this system is going to normalize it with respect to the error from the mean of the data. So simply is equal to the summation of yi minus yi hat squared divided by summation of y minus y, which is the mean here. Okay, so the mean of the data is equal to like the average of all these particular points. So this is 1, 2, 3. So we have a certain type of value here, okay, and we compute each particular value that we have estimated in this particular system here. It's going to be provided, and we are going to compute this particular type of ratio. So this also, you find it in several type of instances, and it gives you a normalized representation to the distance of the estimated values from the actual values, where the actual values are located. So this is an important score, and I would like you to remember it. You can utilize it in the assignments if you wish, but you are not constrained to do that. The mean square error mostly is the one that people utilize. So I have provided also some references to read in this particular aspect, and I have also shared with you one or two links in the page of the performance measure. They are not very long to read. I encourage you to look at them. I encourage you to look at some of the examples of the additional reading that I have posted under this particular module, which is the performance measure for regression and classification. It's a very good set of concise formulas, similar to what I have shared with you in these particular slides. Okay, so since I'm done with the performance measure for regression and for classification, so I would like to ask you if you have any questions before we go to the next part for our lecture, which is support vector machine, which is not also going to be part of the quiz, so it's not going to be part of the quiz. So I can take one or two questions if you have any before I continue with the lecture on support vector machine, which is another component of supervised learning, machine learning model that is not based on connectionist modeling. Okay, so feel free again to email me. I receive a number of emails from students about the lectures and about the slides, so I'll be happy if it is concise, short email. Please do so. And I would like to remind you, students here, attending synchronously and others who are going to listen to this lecture asynchronously, please make sure to only send requests to Piazza only when it is absolutely needed, because the overwhelming number of requests made by students for very little questions, very simple. They are important questions sometimes, and we are happy to respond to them. But because this class is very large, and because we don't have a lot of resources, they are not assigning us a large number of TAs, and because of also my busy type of schedule outside of teaching this course, it overwhelms us. So please make sure to utilize Piazza only when it is needed, and we will be always happy to help you. Even with personal emails, I receive a lot of individual emails from the students, and I am happy to respond concisely to these type of emails, and sometimes even exchange of email, or sometimes I forward the email to one of my TAs to take care of some of these questions. But ask questions. I encourage you to ask questions, even small or large, but without overwhelming the system, because it's a large class again. So take a note of that, and to make sure that we all benefit from these lectures and these facilities that we are using for this course. Okay, so now let me go to another part of the course, which is related to support vector machine. It's a fundamental component in the field of machine learning, and it has been utilized over the 80s and the 90s, and even nowadays for either large set of data or even for small set of data. They have been proven to be very, very powerful type of techniques. And the support vector machine is no other than more sophisticated and optimal representation of the perceptron mechanism, or even better, the Adaline. But it's not a connectionist model, so it doesn't have the shape of computational elements that are connected with each other, similar to the neural network or the Adaline. But it is another type of machine learning model based on statistical type of approaches, and on optimization of certain type of margin between the various type of data with which we are classifying. And against, popular, not popular, but a lot of people think that support vector machine are usually utilized for binary type of classification. This is far from the truth. Support vector machine could be also utilized as multi-classifier, as I'm going to mention in the later part of these components. So because this is a very large set of slides that I usually, the whole set, I usually teach it as part of graduate course. So I'm going to share with you only the components that I feel serve the particular purpose of this course, to give you some ideas on a classifier system that is able to support the classification between two or more classes, but it's different than a connectionist model, which is the artificial neural network. So that's what support vector machine. So let's start on with this set of slides. So this set of slides also has been posted. Okay, so let me go again here and let me do the single page. Okay, so this is, we are going to get till the notion of the kernels here. I will possibly skip a number of them, so I'm not going to talk about the application and the number of the support vector machine properties. So I'm going to speak mostly on the general description of these particular techniques, which is a very powerful machine learning techniques, and I wanted to share it with you in order for us not to be restricted to machine learning, because these type of support vector machine where you have also a lot of libraries on the web related to support vector machine, very powerful libraries and software tools that could be utilized for solving problems using support vector machine. So what are they basically? Okay, so we call them kernel-based classifier, and we will see why we call them kernel. Because we are going to utilize them later on the kernel when the classifier is nonlinear separable space. So when it is linear separable space, we are going to utilize the original version, which I'm going to develop for you in the next few slides. But for nonlinear, we are going to utilize the kernel-based classifier, and we are not going to delve very further on that, because usually support vector machine could be taught as a course on its own. But I wanted to share with you here only the power and some of the application of support vector machine when we are tackling a binary or multi-classifier type of system. Also, one component here that I need to mention, although it is called support vector machine, I mean, that's the origin thing, but also people have used it not only for classification, they have used it also for regression. We are not going to tackle that aspect as well, regression. So, and people call it support vector regression. Okay, so that's also another non-connectionist based model that is used for prediction of a regression component or regression regressor or nonlinear type of mapping. So for those of you who are interested in some of these readings, I will be happy to share them with you on a separate basis. So I can send you 1 or 2 links so that you can have access to some of these things. Simply email me and I will be happy to share with you immediately the reading on these particular aspects. So let's look at the support vector machine and what it does for particular type of system. So we are going to presume here that we have vectors. Okay, so we have, let me see here again for the pencil. Okay, so we are going to have a classification method. So what we have, classification method, we have several type of sets. So each one of these sets, okay, so each one of these sets has a particular type of label. So we have possibly the sets presented by the representation of a dog, and Y1 would be dog. And this is a set of features, and this is the classification related to the cat, for instance. So basically the x's, x1 here, the bolded x1, is simply a vector of features element, and the y1 here is simply class 1 here. Okay, so if we go to xm, so we have xm as a vector different than x1 in terms of their features. Of course, they have the same dimension, but they have different type of representation, and here happen to have ym as being equal to class m. So in this particular problem, we have a multi-classifier system, but each one of them is characterized by its particular output. So we say that the data is labeled as we have seen in the problem in the number 3 and in number 4. We have so far seen only labeled data. What do we mean when we speak about labeled data? It means that we are still tackling supervised algorithms, because we are in the bigger branch of the tree now for the course related to supervised. After I finish with the support vector machine, we are going to tackle another class of machine learning models, namely the unsupervised one. Remember, in the early part of the class, we have talked about several types of machine learning models, namely the supervised, the unsupervised, and the reinforced. But there are also other ones, such as the semi-supervised type of machine learning. So we are not seeing the semi-supervised, we are not seeing the reinforced discourse, we are seeing only the supervised. For the supervised, so far we have tackled machine learning model based on binary classifiers such as the perceptron, the Adeline, and then multi-classifier, multi-dimensional nonlinear regression using multi-layer perceptron system, where the neural network has multi-layers, multi-nodes in each one of the layers. And now we are tackling another supervised machine learning model based on support vector machine. So that's again to summarize what we have seen. So let's suppose that we have all these type of data sets. And this, of course, this is a multi-classifier system where we have multi-classes. In this particular early part, we are going to restrict our classes to only two. Class 1, which is given by -1, and class 2, which is given by 1. So this is, again, a binary classifier, similar to what the perceptron and what the Adeline provided us with that capability. Okay, so we are going to see the major difference between what we have seen in terms of the binary classifier and the multi-classifier system. So this is the general formulation for the data sets for the multi-classifier, and this is basically what we speak about binary classifier system. So these are some of the people that have made major breakthroughs in the 60s, in the 70s, in the 90s, and even recently as the mid-1990s, Cortez and Vapnik have contributed even further to support vector machine in the formal and more theoretical type of framework. You can look at these scientists and you can look at some of their particular publications. Again, for those of you who are interested in the history, I will be happy to share with you the material to support that particular aspect of the of this set of slides related to support vector machine. So what is the basic idea here? Let's understand what we mean by this particular system. So let's first look at the very nonlinear behavior of the system. So let's suppose that we have a data set of data points. Again, this is multi-class. So this is the most general type of formulation here. Okay. We are not going again to utilize the kernel for particular system. Okay. So the idea here, we are going to create a system that is originally non-separable type of system. So system that is, similar to this particular system where data, are, non-linearly separable. So there are no lines or boundary or hyperplane to separate between them, and transform this system into a model with higher type of dimension where the data is separated by a hyperplane, similar to what you are going to discover in the problem number 2. So these type of problems going from linear type of dimension, so this is the dimension, so x1 here, and this is x2, and the system is not linearly separable, so we have to come up with the change of type of data here, so that the coordinates in the new space is going to be higher, and then we are going to end up with phi1 here, with phi2 here, and phi3 here. Okay, so this is, these are the change of a coordinate system where this nonlinear type of separability become separable by a hyperplane. So here we have a hyperplane in this 3 type of dimension. Of course, we are going to lose when we are going to do this type of separation for this particular nonlinear model. And this applies not only again for 2 dimension, but it applies for multi-dimension. There is a video clip that I am also going to share with you in the set of slides, where it shows this particular change of coordinates for the system. Of course, the price we are going to pay is how to create this particular change of variables. And this is where the kernel comes into, and we are not going to go into the details about the kernel representation to map data points to vector of representing with higher dimensional type of feature space. So from 2 feature space to 3 or more feature space, that will provide us with that capability of linear type of separability. This is an important component, but this is for the multi-class and for the nonlinear type of separation. For now, let's forget about the kernel and let's look to the case where we have simple 2 classes for our models, and these 2 classes are linearly separable, and how to provide the optimal distance between the 2 type of data sets. Okay, so we are going to, so I will skip this particular component and let's talk about what is the original support vector machine, because that's what we are more interested on, as I mentioned to you earlier, when we have 2 classes and where we have, this y1, ym belongs either -1 or +1. So this could be 1, this could be -1 or 1. So it depends on the binary type of classification. So let's look at the original support vector machine when it was first suggested, okay? And what is the major idea? Of course, when we are speaking about more than 2 dimensions of the feature space, we speak about, instead of planar, similar to what we have seen in the line and the perceptron, if we have more than 2-dimensional space in the input, then we speak of hyperplane, separating between the various type of classes. Remember, in problem number 1 of the assignment, we have dimension of the vectors, 3 dimension of the actual vector. And this 3 dimension is going to suggest a plane to separate between the data in between the 2 classes. Here, the same case that we are going to utilize. So let's suppose that we have data belonging to either one of 2 classes. We have some hyperplane, again, when we have more dimension than 3, because this particular vector could be of dimensionality higher than 3. It could be of 10. It could be dimension, 20. So when we have dimension to 20, then the planes that are going to separate between the data are going to be called hyperplane. We don't see them visually because we cannot see something beyond the 3 dimension visually, but we can frame them theoretically into the mathematical framework. So suppose we have some hyperplane which separates the positive from the negative samples. Okay, so we have 2 sets of data. The data points that lie on the hyperplane satisfy what is known as omega t plus b. So this is similar to what we have seen. So let's take the problem of the 2-dimension state, which is the simplest type of model. And here we have class 1, and here we have class 2. Okay, so this particular line, when this becomes more than 2 dimensions, so this is x1 here, let's say, this is x2. Remember, this is -1, let's say, this is class -1, this is class +1. We can call them also class 1 and class 0, class 1 or class 2. It doesn't matter. So the data points are located here. So this is very similar to what we have seen in the perceptron and in the other line, but this is a completely different machine learning type of framework. This is a different paradigm, as we are going to see in the next few slides. Remember that the boundary in our system in the perceptron is expressed as omega1 x1 plus omega2 x2 in the problems that I give you in the slides, and also the problem that I posted, addition to the slides, plus the bias term plus theta is equal to 0. Remember, this is no other than this particular curve here for the 2-dimensional case. So this is, ax, y is equal to, so this is no other than y is equal to ax plus b This is the value B when x is equal to 0. When y is equal to 0, this is equal to minus b divided by a, although here a could be a negative value in order to make it in this particular type of location. So this is what we call it, the data point that lie on the hyperplane satisfy omega tx plus b equal to 0, where omega is normal to the hyperplane. So we know that ax plus b, okay, so when we are dealing with the multi-dimension value, so this perpendicular for this particular problem here is given by yt here, which is y1 and y2. So this is the vector that is perpendicular to b. Why? Because when we are utilizing the value that is perpendicular to omega t here, is this to this particular type of hyperplane when implemented here, this becomes equal to 0. And we know that two perpendicular vectors, have the scalar product is equal to 0. So omega is usually the normal to the hyperplane. So when you have a hyperplane, given by this particular representation, omega is the perpendicular vector to this particular hyperplane. See, this is always the case. And b divided by omega is known as the perpendicular distance from the hyperplane to the origin. Okay, so let's look at this in this particular image. Okay, so the next image is very, very revealing to tell us exactly what I was just mentioning in the over the past few minutes. So we have set data 1 here. So this is class 1 and this is class 2, the blue one. Okay, notice that we would like to create a certain margin between these two type of classes. That is our ultimate goal. So this could only happen again when we are dealing with linearly separable type of data. We are going to see the case later on when the data are entangled with itself, are not non-linearly separable type of data. Then we are going to utilize what is known as the kernel. But for now, we are going to utilize the data is linearly separable. So what is our problem here? Our problem, what we want to have, we would like to find the region that is the furthest between a band that is the furthest away from class 1 and class 2. Remember what we said in the perceptron? The perceptron doesn't provide us with an optimal distance between the two type of classes. And as soon as one of the data that is going to be presented newly to the system is going to be provided to the model, then if that data belongs to a class that is close to it, then the perceptron is not going to provide us with the best possible boundary. Why? Because we have seen that the Hebbian learning doesn't provide us with a good generalizer. Remember the problem of generalization? A good generalizer is when we develop a particular boundary from the training data. And then when we are going to utilize the the testing type of data, we would like that boundary to hold. But sometimes the testing data might be stained with noise. So it's going to locate itself very, very close to the opposite type of class. So this is going to constitute a problem because then we need to retrain the system. So what we did, we created the Adeline. The Adeline is a better version of the perceptron, although it doesn't tackle non-linearly separable space data sets, but still it provides us with the optimal distance between class 1 and class 2. So when you see the Woodrow-Hoff learning, the system provides us with good distances from both type of C1 and C2. So we would like to go further than the Adeline. We are not going to use a connectionist model. We are going to use another type of model where we would like not only create a boundary between both of them, but we would like to create a margin. A margin. It's like a margin that we are going to optimize, make it as maximum as possible. So what are going to be the support for this particular area here? It's going to be provided by what we call support elements. So this is one of the elements here that belongs to this particular class, and this is an element here that belongs to this particular class. So we would like to maximize this margin. So the optimization problem that we are going to solve here is going to maximize this particular margin, which we are going to define. So that's the problem of support vector machine. So this is the Adeline and the perceptron. So they are good, they are connectionist model, provide us with certain way for doing the linear separable. Here we would like to go one further step. We would like to have a whole margin of space that separates between the data. Why? Because sometimes some of these particular data might reside in this particular location. And if we are not separating the data by this particular margin, this particular type of data could belong to this. So for instance, if we don't have this optimal region, this data value here might be given as belonging to this particular class. Okay. However, by doing this particular region, empty region of space, it's like a frontier between two countries to avoid, skirmishes or to avoid certain type of friction between tribes in that particular region. We create this region and we would like to maximize it. The problem of support vector machine, or the formulation of support vector machine, is maximizing the margin. Maximizing the margin, what does it do? It gives us generalization. So the larger the width, this particular margin, then we can situate some of these particular values in this particular location without being afraid of invading the space of this particular type of data set here. That's why we would like to do it. So one of the problems that we are solving with the support vector machine is improving the generalization. And I would like you to remember something when we spoke about Adeline and perceptron. When we spoke about Adeline and perceptron, we said Adeline is a better version of the perceptron because it has learning capability that is based on mathematical formulation, which is the Woodrow-Hoff learning procedure, which is like the gradient descent for the multi-layer perceptron, which is a mathematical formalism. For the Hebbian learning, we don't have that mathematical formalism. It's based on the Hebbian learning, which is somehow an ad hoc way for giving the weights or assigning the value of the weights. And that's why we spoke about better generalization of the Adeline than the perceptron. So here we go even one step further. Support vector machine is not a connectionist model, so it's not an Adeline, it's not a Madeline. It is a machine learning model that is based on the maximization of the margin between two data classes. So our problem here is an optimization problem, similar, quote unquote, to the development of the Woodrow-Hoff learning, but here this is not a Woodrow-Hoff learning. We are maximizing the margin between two type of classes. And that's mathematical formulation that we are going to look at in order for us to find out the benefits of the support vector machine. So support vector machine are excellent type of tools that provide us with this whole margin separation that is going to separate between classes. So even if your class falls into here, we are not afraid that this class, the blue one here, is not going to fall, and people will say that it belongs to the other class. Even if we look at it in this particular region, we say that this particular class has its own type of boundary, and the margin has prevented us from assigning one class to the other class. So as long as we maximize this margin, elements that are located here, from the blue and here to the blue, or the reds here and here, are not going to be looked at as elements of another margin. Why we do this? Because again, sometimes a system might, in the future, when we do the testing, when we implement commercially this type of problems, it happens that certain type of values might be located in different regions than this particular type of classes. And although they might belong to the red one, but they are located in a region that is close to C2. And the C2 might say, oh, it belongs to me. Okay, so this is when we create this margin, the system is not going to do that. It says that, oh, we have a boundary between two of our families, and we are not going to approach that boundary because each one of us belongs to the other particular class. Okay, I hope you get the points here, why we are trying to create that particular type of margin. So instead of dividing by a certain type of boundary that might not be optimal, here we are not creating one single boundary, we are creating a full margin. So let's look at this particular curve here. This is omega t x plus b equal to 0. So this is basically the usual boundary that's similar to what we have seen in the perceptron, but we go further and we would like to improve this particular margin. What is this margin? What is the value given by this particular margin? So this margin is no other than given by the value of b divided by the Euclidean distance of omega. Remember that omega is a vector. That's why we put it as transpose. That's it's omega 1 x1 plus omega 2 x2. Okay. So plus omega n xn in hyperspace. Okay. So when we created, omega is represented in vectorial form as composed of omega 1 and omega n. Okay, and we simply create the transpose of this vector in order to have transpose times x plus b is equal to plus 1, because this is a scalar representation. So it's omega 1 x1 plus omega 2 x2. So this is basically what we have in this particular type of region here. And we are going to look at the optimization problem, how we are going to maximize this margin. But what is the width of this margin? How can we find the value of this particular margin here? So remember that this is equal to the distance from this point here to this point here to the center is given by b divided by omega. But the distance which we would like to optimize is going to be equal to this particular region. But that particular region is given by 1 minus b divided by omega minus 1 minus b divided by omega. Why we have that? Okay. So remember that this is the value here. This is the value of omega tx plus b equal to 0. And this particular line here, curve, is given by omega tx plus b equal to minus 1. And this one here, h1, is given omega t plus b equal to plus 1. Okay? So here we have b divided by omega at the center. So if we move it to this particular location here, we are going to have minus 1 minus b. Why minus 1 minus b? Because of this particular element. So it's no longer equal to 0. It's equal to minus 1, the value here for this h2. So that's particular value here. So that margin is equal to this particular distance, which is given by this element here minus this element here, and it gives us all this particular margin. Okay, so the distance here is equal to b divided by omega, but the distance here is equal to b minus 1, and here it's b minus 1 for this particular version, and we can look at it. So we have 1 minus b for this area here, minus 1 minus b for the area that is closest to the origin. Okay, and when we compute this, we simply obtain this as equal to 2 divided by omega, which is the Euclidean distance. So this is distance from h1, again, let me repeat it. This is distance from h1 minus this particular distance, and it provides us with this particular type of margin. Okay, so distance from H1, distance from H2, it's given to, this is the fundamental value that we are looking for. We would like to optimize this value subject to the location of the data in this region, which we labeled it by -1, and subject to the location of the data in this region, which we labeled it by +1. So all of the elements here belongs to the +1. And why we call it support vector machine? Look at these two data here points. This, we consider them as a support for this hyperplane. These are support for this hyperplane, the second one, which is H2. That's why we call it support vector machine. So machine comes from machine learning, and support is support vectors. So they are support vectors. So because vectors in the hyperplane, and they support those two hyperplane H1 and H2. Remember that H1 and H2, although here we see them as lines to facilitate for you the visual aspects, but usually they are hyperplane. So they are support vector machine. So that's why we call them support vector machine, machine learning, and vectors to, the location of these points in the hyperplane of the attributes of the separable type of data. So we would like to optimize. What do we mean by optimize? We would like to have this as the smallest possible. Why? Because if this is the smallest possible, then this is going to be the largest. Remember that we would like to expand that band between C1 and C2, between class 1 and class 2. So minimizing omega, maximizing M. So for the linearly separable case, the support vector algorithm simply looks for the separating hyperplane with largest margin. So we are tackling the linear case here, the linear separable case, where the two classes are separate by a hyperplane. So now we would like to maximize M, but this is going to subject to a certain, this is the performance metrics that we need to minimize. So we would like to minimize, but we would like to do it subject to the products of this class yi, which could be 1 or -1, times omega t xi plus b greater or equal than 1. What does that mean? It means that we have to have this minimization of maximization of the margin, which means minimization of 1 divided by omega square, subject to these vectors that are located on x1. Look at this particular vector. So it's omega t plus b, so +1 equal to +1 here. Omega t x plus b is equal to -1. So we reflect that particular type of representation into this particular format. So yt, if it is positive, then we would like it to be greater than 1. So it is further away from this particular elements. And the other one, when it is equal to -1, we would like it to be further away than this particular type of value to have the constraint of the system that represents this H2 and this H1. So that's the problem that we would like to solve, subject to these particular type of constraints. Okay? So as I promised to you early on, so this is, the formulation, mathematical formulation for this machine learning, which is used mostly for generalization. It's not a neural network-based system. It is based on support vector machine type of approaches, and it is used mostly for generalization. We are looking at it at this particular stage in the form of separating boundaries and maximizing that boundary between class 1 and class 2. So we are going to, there is a possibility that later on we expand this to multi-class, not only to classes, but also we can apply the support vector machine not only to linearly separable system, as we have seen in this particular representation, but for non-linearly separable type of cases. Okay, so I'm going to stop here. I have put the mathematical formulation, and we are going to try to solve this problem mathematically. Next time I will give you the solution, so we are not going to go into the intricate aspect of the system, but we will try to resolve it. And and I would like to give you the solution, and then we'll tackle the nonlinear separable space, and we'll talk a little bit about the kernel. So let me look at questions from your colleagues here. If we have a new C1 entity inside the margin, would this be a new support vector for H2? Would this alter the distance for H2? Good question. So this margin is mostly used to have, very, very big type of band as much as possible. So if we have a new values that are close to C1, we always consider it that as part of C1. We are going to see that we are going to have more flexible version of this very restricted type of margin. So your answer, we are going to, your question, we are going to look at it next time when we are going to tolerate some element of C1 and some element for C2 without changing the overall representation of the support vector machine. So using that particular representation, we are able to do that. Some elements that are close to C1, but they fall into the margin. What should we do about them? For one particular element, we are going to restrict the margin. Sometimes no. We say that that might be a little bit of an outlier and we can tolerate it. So we are going to tackle that aspect in the next lecture. Why is I in the bottom formulation to I and not N? So let me see here. Which slide is this? Can you tell me which slide is this? Why I is where? I is in the bottom formulation to L. Here. What is L? Why is I is in the bottom? Okay. Oh yeah, L here, simply L here means that it's the class. So here we have two classes. That's what we mean by that. Okay. So yi here, it means it's either class 1 or class 2. So this basically is equal to 2. Okay, so it's 1 to 2. Okay, so that's what we have here for this particular one. Okay, and this particular version, for yi, is falling for this particular representation for this particular system. So for each one of this particular system, we have this representation. So in this particular case, y is equal to 2. Does that respond to your question? So it's not the dimension of the system. And this one here to be a little bit more, accurate. So this is omega t x plus b. So this is, this is a typo here. So we have yi. So this yi could be 1 or minus 1. So for each one of them, it has to be greater than 1, which is going to be within that support vector machine. Okay, so that's basically what we have for this particular equation. And next time I'm going to provide you with the representation of this system here, and we are going to take it later to express what we want to do when the data is restricted within the particular type of boundary. Okay, so again, remember these two type of elements. So this is the performance index, and this is particular subject to this particular type of condition. So this is a constraint, if you would like to call it, and this is mostly the support vector location for some of these data that belong to either one class or to the other class. Okay, yes, so that's what I wanted to share with you for today. So I'm done with the set of lecture today. So I will post the material, as I mentioned to you today, for the components that for the test quiz that I provided yesterday. And I will post also the tutorial lecture that was provided by Mahmoud along with the documents for that tutorial. Please look at it if you would like to learn more about classes of systems. And if you have any questions, again, feel free to email me. One more reminder, please minimize the use of Piazza for very, very elementary questions to avoid an overload on me and the TAs. Thank you very much for attending today's lecture, and talk to you on Monday. Okay.